Orleans virtual meetup number 5. I'm trying to play Richard Asbury, who is doing a much better job of hosting these things, but we'll try not to drop the ball entirely. So today we have Gabi Kliot who will be talking about Orleans streams, what that is, why we need to build this thing when there are so many things out there that have streams in the name, what it's useful for, how to use it, how to extend it, so all that kind of stuff. So I'll hand it over to Gabi. Can anybody hear Gabi?
Yeah, we can't see the stream.
So many things. Can you hear Gabi now?
Can you guys hear me now? Can you
Yes.
guys hear?
Yes. Yeah, I can hear.
Excellent.
Okay, great. Okay, so let's start. Okay, so I'll tell you. Someone can hear myself. Okay. So I'll tell you what Orleans streaming, and of course this is a joint effort by all the people on Orleans team, and I'm just the one who is presenting, but there's much more people.
Sorry guys, Gabi, I can't see your screen. Could you please share the presentation?
I can say it. Okay.
I can see Gabi's screen. Anybody else can see it? The slide?
Oh yeah, sorry. Yeah, I can see.
Just
now.
delete. Okay, excellent.
Okay, great. So let's start. So I'll start with some. Retrieval of this data, delivering into processing logic, and scaling this processing logic. So that's what we are trying to achieve as well. This is I call this decoupling in time, because you may be producing the data now and maybe also processing it later. And the different scenario is, imagine a chat room. People join the chat room. Someone publishes. Just write in the chat, and you just want to subscribe to a stream of messages from the chat room, and you don't want to care who else is subscribing and who else is producing, and producers don't need to know about the consumers. Okay, just a second. So this I call decoupling in space, because they don't know about each other, and then maybe some of them failing, restarting, there are crashes, but they don't care. Okay, they keep receiving and producing this data. So this is the motivating scenarios that we started with. Now, someone may ask, hey, like, why do you need to build yet another streaming platform? There's so many streaming platforms and technologies out there. I just use something that already exists. So let's look what exists out there. So basically, you have two sets of systems. You have a system that can durably store data in some, we call them queues, persistent queues, like Kafka, Event Hub, Service Bus, maybe Azure queues. That's great. That's a very important piece of technology, but by itself, it doesn't even address the compute part. So for compute, for processing this data, you have all those other systems like Azure Stream Analytics, Apache Storm, Apache Spark Streaming. These are great and very useful, but if you look what you can do with those systems, inherently, you can define something that's called data flow graph of operations. And you apply those operations on all your data. And it's usually uniform set of operations that you apply in the same way to all your data. So it's some set of transformations, filtering, aggregation operations, and the system are very efficient and great. They're great because they were built to be optimized for processing large volume of relatively similar data in a similar way. And they also limit your expression of what you can do in this processing. And because they're limited, they can be very efficient and process huge amounts of data. So that's great. You can build those systems, but that's not what we're targeting. We're targeting different set of systems for which streaming is very useful, which is interactive workloads. So in interactive workloads, you may have very diverse data, and I'll show you examples in a second. You may have very diverse data, and different pieces of this data may require very different processing. And this processing may potentially be stateful, or may not. And maybe as part of the processing, you're also generating side effects. You maybe need to make some external call to some completely different service. Or your processing may depend on a condition which is not present, which is not part of your data. So you cannot solve them with those unified data flow engines. So what are the scenarios? So let me describe like this one big scenario. Imagine you have a universe of users. Maybe it's all like players in Halo, maybe it's like a Cortana-style users or Facebook, social, complete great application. And different users are interested in different things. So some are interested in weather in their specific location. Some may be interested in sport events. Some are interested in flight statuses. Okay, and you want to process these different streams of data in the context of every user and do something very different in each of those cases. And as I said, then sometimes the processing logic may depend on some external condition which is not part of your data. So you need to be able to check that condition and involve the processing. And maybe sometimes you need to create, not only produce derived data, you may also need to make some external call, which is like HTTP call, and then change something completely outside your service. And not only that you want diverse processing capabilities, and also your topology may be changing. So users may come and go and may express interest in new pieces of data. So I'll call it new streams of data. And then they may decide I'm not interested anymore. So both the elements that are processing the data, but also the data sources themselves that come and change all the time. And not only that, the processing logic itself may be evolving. So think about the following example. You have in Halo, they try to find cheaters and like remove them from the game. So someone is making some operation in the game that allow him to cheat. They collect, all important operations in the game, put them in some cheating detection service, and this service tells like, okay, those users cannot play anymore. So let's say you're building this service in this streaming platform, so you have a set of rules that you apply to incoming events that you analyze, and then let's say you detected some new ways that people are cheating, because people always find new ways to cheat. So you found this new rule, you want to go back and change your cheating detection logic with this new rule, and you want not to disrupt your current service that always running and analyzing the data online in real time. So you need to be able to go back and update your logic without taking it down. So all those were real scenarios. I'm not like inventing anything here. These are all real requirements that we had. So we looked at those scenarios and we basically came up with like 4 architectural requirements. Let me tell you about those. So first, we want a system that will allow flexible stream processing. What I mean flexible is basically we don't want to limit how you express your processing logic. If you want to express it as a data flow, kind of like in those other systems, great, no problem. You want to write some functional F#, great. Declarative queries, no problem. But if you want to do just general imperative compute and do whatever logic you want to process the data, you should be allowed to. Second requirement, we want to support dynamic topologies. So by topology, I mean there's data. The data is multiple streams, and the new streams come and go, and new processing elements come and go, and this whole collective topology needs to be able to evolve without taking the system down. So this, let's see in this example in red, this is some hypothetical data flow. Okay, like I have some stream and I want to group it by, select some element of this data, and maybe like change it, and maybe do some averaging and filtering, etc. So that query, that data flow, sorry, not query, that data flow, you can deploy it in one of those systems I mentioned before. But now imagine you want to change the threshold in the web. How do you do that in those systems without taking them down? Or maybe you want to add a new select element and produce something else in addition. And or maybe you even want to add like some new element to that data flow. We want to allow those things. Okay. So third is what we call fine-grained stream granularity. So collectively, you have huge, like in this example of users, all the data for all the users is one huge stream of data. But we want an ability to say each individual user, it has its own stream, and be able to talk about that stream in this fine-grained granularity. Why is it good? Because then I can change. Then I can shape the way the stream behaves differently. Like some streams may go through different lower-level delivery technologies, and we'll talk about that in a second. Some streams may have different semantics. I want to be able to shape and change each of the streams and each of the processing elements separately. It means this small stream needs to be a logical abstraction in our platform, as opposite to one huge pile of data, which you always can process only in the same unified way. And of course, we're here in the business of building distributed systems, so of course this whole thing needs to be distributed. And I don't need a reactive manifesto to tell me how to build distributed systems. We all know how to build them. It's hard, but they need to have those properties: scalable, elastic, reliable, efficient, and of course responsive. We want to receive this data in near real time. We're talking about seconds, hundreds milliseconds, even sometimes tens of milliseconds, and be able to process and react to those events. So these are the 4 architectural requirements for solve that, and how Orleans streaming is helping us with that. And I don't know if there's any questions at this point. Okay. So this picture is actually kind of summarizing what I said before. Is how we look at it architecturally. So the data comes from some data sources, okay, and those can be external, like calls from your clients coming as HTTP calls, like in the devices example. They can be calls from another service, or this can be something that comes even like from some pre-populated data in some queues or whatever. Okay, so the data comes from that and generates a stream. So the blue arrows are those individual streams, and the red and the red elements, these are the processing elements. So in Orleans' case, this will be Orleans grains, Orleans actors, piece of logic. Okay, and those processing elements, as we said, they can have any logic to process those streams, whatever. And the blue lines, the streams, they can go over different technologies. Some of them, like let's say Azure queues, Kafka queues, event hubs, direct TCP messaging. Okay, so each one of those we call them individual stream, and of course this whole thing together is like streaming topology. But we're talking about each of those individual streams. So how we approach that scenario? So in Orleans, we always start with like, okay, so what is the programming abstraction first? So we came up with that concept of virtual streams. And for those who are familiar with the virtual actors in Orleans, well, it will sound actually pretty logical. So what is the virtual stream? So it's a programming abstraction. It's a logical abstraction. What makes it virtual? Well, it always exists. You don't need to create it, and you don't need to destroy it. It can never fail. You can always get handle to it. Getting handle is as simple as like get stream, which is kind of like get grain, and it's always a local operation. You just get a logical handle, logical reference to a stream. Streams are identified by GUID and an optional string. So the string allows you to have kind of stream namespaces. So this is kind of similar to Orleans. Let's say you have, right, in Orleans you can have user grain 7 and chat room 7 and player 7. This is the same number, but different grain types. So the same you can have with streams. You can have chat event stream 7, and you can have device stream 7 and something else 7. So you can define those namespaces, and the GUID is unique within that namespace. And this abstraction, so this is how you program against this abstraction, but there could be different implementations to it. So we need to allow you we need to allow different implementations which will shape the semantics and the behavior of those streams. So let's say sometimes the streams go over durable queues, and sometimes direct messaging. They have different semantics. Like we will talk about delivery semantics and the ordering semantics. This can all, we should be able to shape and change those and determine the behavior of those streams by just basically saying this is stream of through configuration, saying this is stream of that family of behavior. And also we want to have a pluggable model where someone else can come up and add new behavior for streams. And we call the provider model, just like in Orleans we have providers, so we'll have stream providers. So let's look how this virtual stream abstraction looks like in the code. So it's actually pretty familiar to you. This looks pretty much, for those who know RX, reactive programming in C#, this is basically distributed RX. Okay, so why? So well, it had to be distributed because we wanted to work across servers, right? And that also allows you to decouple the production and consumption events both in time and space. So how does it look like? So let's say you're a consumer of a stream. You're interested in a stream, right? So to consume, you need to say, I want to observe that stream. So you implement an interface, I observer. Actually, it's I sync observer. Okay, and you just say this is the methods to process the stream. To producer who produces in a stream, he thinks he's talking directly to consumers. So he is invoking methods on iObserver interface. But of course, he's not really tightly coupled to consumer. He talks to something that pretends to be consumer, which is this virtual stream. Okay, and to consumer, he just needs to subscribe to a stream. So he subscribes to iObservable, something that can be observed. Okay, he thinks he subscribed directly to producer, but of course he does subscribe to the stream. And the stream itself, that's what we implement, right? That abstraction. Okay, let's look at the. So what we did to RX, so RX has iObserver and iObservable. we made them asynchronous. We said we have async observer, async observable, and all those methods now return tasks. And that's basically, like, logically, that's the only deviation. And we had to add some little bit more hooks and add a little bit more tweaks. And I'll show you those. But at the high level, this is the main, like, deviation from the standard track. Just make it asynchronous. Okay, so let's look at the API. On the client, handle to the stream provider. And for now, just think about it. This is a factory for streams. It's just like in grains, you have grain factory and you get a grain reference. This is the same. You get factory for stream. This is stream provider. And you say which provider you want. And then you just call it get stream. And you're passing the identity of the stream, which is some kind of GUID and optional namespace. And what you get back is async stream. Both those calls are local. Nothing happened remotely. No messages were sent. And so this async stream is quite similar to grain reference. Okay, it's a logical handle. It implements both async observer and async observable. So you can use the stream both to produce and to consume from the stream, and to subscribe and consume from the stream. So what producers can do? He can just call on next, on completed, and on error on that stream. On next will just produce event to the stream. Now you may ask, like, what does it mean to call on completed and on error on a stream? Does it mean like I'm finishing the stream, I'm breaking the stream? So here because we wanted to have this virtual abstraction that streams always exist, we actually do not prescribe what would happen when you call on completed and on async. If a producer call on completed and on error, it will call on completed and on error on the consumer. Okay, but it will not change the state of the stream. Stream just stays the same. Stream is always alive. There's no way to kill the stream or break it. The consumer may decide what he does upon it. Maybe he decides, oh, if the producer signaled me that the stream is completed, I will unsubscribe. Maybe. But we don't change the state of the stream. Now, so how consumer uses the stream? Well, he just subscribes. Because stream.subscribe async, it passes something that can process this logic, which is async observer, and it gets back a handle. I'll talk about the handle in a second. So you can either pass async observer is an object that needs to implement that interface on next, on completed, on error. And alternatively, you can also pass just lambdas, just like a success lambda, error lambda, completion lambda. And there's a couple of more overloads what we added to subscribe async. So what you get back is the handle. The most usual thing that you'll do with the handle, you'll store it, and then later on you can unsubscribe for it. So unsubscribing through this handle from the stream, basically you say, I'm not interested anymore. It's kind of like async I disposable. But there are also a couple of other things you can do with this handle. So I will let's just keep it this way. And what is important to note is if the subscription that we made, it's not for this activation only. It's made by this grain, so it will stays there. The subscription stays alive basically forever until you explicitly unsubscribe. So this activation, subscribe, and then later on was deactivated and died, and an hour later, new message was published on that stream. This grain will be reactivated, and new activation will stay subscribed to the stream and receive this new message. Okay, so that's important to remember. Subscription are for grain and not for stream. Okay, so let me go a little bit more quicker. So first, multiplicity. So you can have multiple consumers, multiple producers for the same stream. When producer publishes, all consumers, of course, receive it. You can subscribe multiple times and then manage each subscription separately. There's no limitations on that. Okay, now let's talk about another extended feature, which is called implicit subscriptions. So usually, like in the way I showed it before, you need to explicitly subscribe to the stream. And you will do it based on some external trigger that you receive. Let's say I'm a user in this chat application and I'm joining a chat room. So when I'm send join chat room message, I'm going to explicitly subscribing to chat stream. So that's great. Sometimes you just don't want to add this control message which causes you to subscribe. You just want basically say, hey, like in the device example, I'm a device that generates data, and whenever there's a data, just create a new actor that will just automatically receive that stream. Okay, I don't want to send first a control message saying, actor go and subscribe. Okay, so it just simplifies the program, that the stream will just automatically land on the right grain. So we allow that with the usage of what we call implicit stream subscription attribute. You basically can annotate the grain class with this attribute saying this grain is interested in that stream type, and then the GUID of the stream will be matched to the GUID of the grain. So let's say there is a stream my device stream, and it will and then stream my device stream 7 will automatically land on device grain 7 if that device grain had this attribute. Okay. So that was basically about how to program. There's much more capabilities and details, and it's all in the documentation that was, by the way, updated just recently. There's a lot of documentation now online. So what are stream providers? So the stream providers is extensibility points to shape behavior and semantics. You may have some streams that deliver, as I said, through TCP, some through Azure Queues, the event hubs, different other technologies. What about delivery semantics? Like, how am I guaranteed that all the events will arrive or not? Is it best? Is it at most once, at least once? So here we made a very global decision for all the stream types, for all the stream providers. Every stream provider can decide what it is messaging guarantees. So, for example, we in Orleans ships now with 2 existing stream providers. One is called simple messaging stream, and one is Azure Queue stream provider. So, what is simple messaging stream? It just uses the regular Orleans messaging for delivering events. When the producer publishes, it gets back a task. That task represents actually the delivery and processing by the consumer. So the producer can await that task. If he waits and it's successful, and then they publish the next message, well, great, you got exactly once and ordered. But let's say if this task breaks, it's up to the consumer now, the producer now to decide: does he retry? Does he break the order? Does he send again? So he can shape the whatever semantics he wants in his application this way. Maybe a more interesting example in Azure Queues. So when you publish to Azure Queue stream from the producer side, it just queues it puts it in the queue. Okay, so it's stored reliably. Okay, now Orleans streaming will read that message from the queue and try to deliver. So if the delivery failed or processing failed, we will not delete that message from the queue. And Azure Queues have this nice feature that if you didn't delete the message from the queue, it reappears. So the message will reappear after some couple of minutes, or I don't remember exactly how much, and then we'll try to re-deliver it again. So in the failure cases, you will receive that message more than once. So Azure Queues inherently don't guarantee you FIFO order in the presence of failures. That's fine. That's what you did. You use the Azure Queue stream provider. If you want another guarantees, well, you should have a different stream provider for that. And stream provider have different batching, back pressure, etc. Okay. So as I said, we currently have a simple message stream provider, which uses Orleans messaging, and Azure Queue provider, and we're working on Event Hub stream provider. It's in progress. Okay, maybe I'll talk. I already talked about semantics. And this applies across all the stream providers. Once you subscribe, you're guaranteed to start all the events that were generated after you subscribe. So this is actually a very strong guarantee that from when you subscribe, you will receive all the events. But for individual delivery, as I said, it depends on the stream provider. And same on the ordering. And there's also a way to define application order. So when you publish an event where we added an overload, it allows you to pass a sequence token, which is basically some ordering token that allows you to order your events on application level. So we don't look at that token, we don't care about the token, like from a Orleans runtime perspective. We just pass it together with the event. So the producer, you attach those tokens. It should be some kind of serial numbers, sequence numbers. And on the consumer side, you can reason about those, reorder and whatever. So that way you can completely do your application level ordering. Another concept that we have is called rewindable streams. So usually when you subscribe, you just say, I want to receive all the events that were generated from now on. But it's also very useful to be able to say, I want to go back in time and reprocess some events. Subscribe from an hour back. Well, it may be just because you didn't even know that you needed to subscribe, and then sometimes later on you find out. Or it's also very useful for in some recovery scenarios. So we have this notion to rewindable streams. How you program it? So basically, when you subscribe, you say subscribe as in, you pass the token. You say I want to be subscribed from that point in time. And implementation depends on stream provider. Some stream providers allow to go back in time, and some not. The simple message queue provider does not, and the Azure queue provider does not. But Event Hub provider, for example, may have, or other provider may have this capability. So one very useful usage scenarios for recovery scenarios. Let's say you want really you're interested in very strong guarantees for your processing. You don't want to lose any event. You process and you change your internal state in grain, and if you can checkpoint after every operation, that's great, that's easy. But sometimes there's just so many data, you don't want to checkpoint all the time. You want to checkpoint periodically. So you checkpoint every 10 events or every minute, but you may fail, and then when you reactivate it again, you want to go back and resubscribe and replay all the events from the last checkpoint. And there is a nice article by Jay Krabs, which is a guy who was behind Kafka and Stamps and LinkedIn, questioning the Lambda architecture. And I recommend people to read this blog. All basically talks about that scenario exactly, that you can achieve this strong Lambda, instead of building this Lambda architecture, you can achieve strong consistency for your process, for your CEP systems with this pattern. As I said, so currently neither simple message stream or Azure Queue are rewindable, but we are working on building a rewindable stream. Okay, let's shortly talk about implementation. We usually don't talk much about how, in our meetups, we didn't talk much about how we do things actually, but I think it's important that people understand a little bit how it works. So when you subscribe to a stream, you pass this async observer, but when we send a message, it needs to arrive to the stream, and you don't do that grain, and you don't see any grain method that necessarily sees that. So that's because internally within the runtime, we dynamically add a hidden grain method, which we call grain extension, which will receive that grain call and deliver it to your application async observer. So there's this mechanism of grain extensions. The more interesting involved is how we build those providers for queues. So we have a base class, which can be used for implementation of providers, for this queue-based providers, which we call persistent stream provider. And what it has inherently is a couple of components. So the most important one is pooling agents. So we need to basically collectively, from all the silos, be able to read events, right, from all those queues and deliver them to grains. So we need to have some kind of distributed microservice, okay, which will be partitioned and highly scalable across all the silos, and so that those agents will collectively read those events, okay. And you need an ability to say when stream is published, to which queue it goes, how I map streams to queues. So there's a notion of stream queue mapper, which does that. And then you need to say those queues, how they're balanced across agents. Which agent uses, pulls from which queue. So that's a stream queue balancer. And in addition, there is this component called queue cache. So what that solves is the following problem. Let's say you are this agent, you're reading events from some queue, and there is multiple consumers for the queue, and you start delivering. Some consumer may be slow and some are fast, and some streams are going very slow and some streams are fast. You want not to have this delivery process be tightly coupled, because you want to be able, to those who can consume fast, you want to deliver as fast as you can. For those that are slow, okay, let them be slow. So this IQ cache is this internal data structure that allows us to decouple consumers from producer, to decouple different consumers and deliver each one separately. And then let's talk a little bit about back pressure. So usually streaming systems come with some kind of back pressure. So what we do about it? So once we introduce this intermediately with this agent that needs to read events from the queues and deliver to consumers, right? We need to answer two questions. So first, how do we do back pressure from the queue to the agents, to the cache, and then from the cache to the consumers? So from the cache to consumers, it's very simple. Every message is delivered by this pooling agent by using Orleans messaging, one at a time. So it just sends to this one consumer message, awaits it, and sends the next one. So it's one at a time. So there is no issue there. It will not overflow the consumer. So you get the back pressure natively from using Orleans streaming. However, we said that you can have slow consumers, and if you keep bringing data from the queue, you may explode this cache. When do you stop? So this is where we have a built-in back pressure mechanism to detect. Okay, I'm bringing events from the queue to the cache, and some consumers are slow. So now I cannot bring any more, because otherwise my cache is it's full, and I need to throw something which was not delivered yet. So there is a built-in mechanism that will slow the rate of delivery and adjust it, and then increase it back, etc. So this is all built within these pooling agents. Okay, so if you want to write more stream providers, what can you do if you want to extend? So the simplest thing first is to look at the existing stream provider and say, hey, can we just make that property configurable? Let's say, or can we shape how the queue sizes or cache size or different properties? So that's actually no, you don't need to write new stream provider for that. You just need to ask us, hey, can we make that property of the stream provider extensible? And then even better, submit a pull request, and we'll just add that. But of course, sometimes you do need to write new stream provider, and for that we came up with this model of these queue adapters. So what we're saying is, for a lot of those queuing technologies, basically you have all those same problems. You need these agents, you need this mapping of queues to streams, and then balancing and back pressure and all this stuff. And the only thing that differs is the physical queue from you're reading from. So you can write this queue adapter, which abstracts away only the specific queuing technology, and then use this base class. And that way, it should be very easy to add new stream providers. And there have been already people who I think are trying to do that right now. Okay, so this is my last slide. Sergey been signing me every 5 minutes how I'm running out of time, but I think I'm fine. Okay, so what is next? What we're building, and where we would love to work more with you guys. So first, what we're working on now is event hub adapters. So there's basically, we look at it like two ways. First, we can start with some simple event hub adapter just to be able to read things from event hub and store an event hub. And then a more complicated rewindable event hub adapter, which will do all those complicated stuff that allow to go back in time and periodic checkpointing. And so this part is what we are actively building here. And we already have a lot of those pieces working, but it's kind of tangled with our other code, which is not part of Orleans, with services code. So we need to untangle it. And so this is work in progress that is actively being done. In general, like if you look at the whole this Orleans streaming project, when we open sourced Orleans, or even when we just made an SDK like a year ago, by that time, Orleans was already in production for like a couple of years. So we already delivered kind of very stable and used technology. Streaming is something we're building now, okay? We have usages of it, and certain parts of it are already very stable, but inherently, this is something that is like work in progress. Like I call it, I would say that currently I look at Orleans streaming as like version 0.9. Okay, there is things are still changing. The public APIs are most probably pretty stable, and I don't think we'll be changing them a lot. Maybe some small tweaks here and there, but they're pretty stable. But specifically, things about the Q adapters and this whole back pressure, some of those things may be changing. So this is why it's a great opportunity for you guys to impact it, because it's not like it's already been built and you coming back and change that. If you work with us together and to improve things here and shape how this will look like, I mean, this is now the right time. And specifically, we wrote a couple of things that might be interesting, but there's more. Well, so scalability, performance improvements. For example, now we can easily support up to like hundreds of consumers per stream, but it will not work for like thousands. The reason is because the way we implement, basically, we have this component called PubSub where we store for every stream who are the producer and who are the consumers. And the way it's implemented in Azure Table is basically one row for every stream, and there's just a limit how much you can store in one row in Azure Table. So there is opportunity to build a much more scalable PubSub system, if we want to support the scenario of thousands of consumers. Of course, building providers for more queuing technology, Kafka, SQS, RabbitMQ, etc. Implicit subscription now, as a note, it's basically you map a stream ID to grain ID, but there's also some interesting scenarios when you would like to maybe map a certain stream based on the content of the data. Maybe you say like, stream of those type has a specific header, and you need to deduce that from, you need to kind of partially, at least partially, decode it in the spooling agent and decide which stream to subscribe. And in custom data formatters, like basically you say like the data arrives through the stream, and I want the system to like reformat it in some other format and deliver it in something else. So things like that. And like programming model, as we said, we didn't want to prescribe any specific programming model. That doesn't mean that there is no desire to build some interesting programming models on top of that, right? So if, for example, building some kind of declarative workflow language or some API that will be automatically kind of compiled, if you want, into actors and grains and streams and executed. That's very interesting. We've been thinking about that. We didn't do any like actual development on that, but it's definitely very, very interesting. And this is where your help, your input will be tremendously helpful. So I think I'm done.
Okay, so we'll get to questions. I was answering questions on your behalf, thinking that you'll probably go over planned time anyway, but I left a couple deferred for you. I'll start with those, and then people just chime in. So first, John Cuttinghorn is asking kind of more architectural question. How should I think about architecting my application? Should I have one stream per device? How should I organize my streams? What should be sort of the guidance there?
Yeah, that's a great question.
Yeah, so we think of those streams as kind of like with actors, right? Like, what should be an actor? Should there be actor per user? And we say, yes, you want like actors to be kind of natural entities, and you want a lot of those, right? And each one relatively small. So the same for streams. You want a large number of small streams, stream per device. Yes, usually.
That sounds good. That feels right.
It's possible to define like a stream of all the devices, for example, and then do something aggregated on that. But it is currently with what I said, like the limitations, for example, of how much producers you can have. Like if you have one huge stream of all devices, when like million devices, it will run currently in a number of limitations. So at least the current state of implementation that you're supposed to have relatively small streams, a lot of them.
Yeah, so I could use implicit subscription then because I was already planning a grain per device, so sort of 1 grain, 1 stream, 1 device kind of thing.
Yes.
Excellent. Oh, that sounds really good. I can't wait to try it out. I'm currently trying to think my way through how to create a emulator to sort of emulate load for these devices, but actually the implementation feels like the easiest bit right now for me.
Great.
Awesome. Thanks very much. This is seriously cool.
Excellent. So another question was from John Nazaria. I'm not sure how you're going to answer it. He literally said, so linearization is guaranteed over the default stream provider? Question mark. Linearization is default stream provider.
Well, so first there is no default. There is a simple message, the one that goes messaging, the one that goes through Azure Queue. There is no default. Linearization. So in the simple message queue provider, as I said, basically it's up to your usage code, how you produce the events, to decide whether the order of events is 5 or like whatever you want to call it, sequential order or not. If you produce an event, the task represents the delivery and processing by the consumer. So if you read the task, you know it was processed. Now you publish new event after you waited the previous one. Yes, you got FIFO, you got linearizable order. If you decide to publish like before you're waiting, well, it's not guaranteed. If the task breaks, you don't really know if it arrived or not. So it's up to you to try to resend or not. And you can use those sequence tokens to build maybe something above that, if you wish. Okay, so I hope that answered the linearizable question.
So any other questions? We'll just jump in.
So is there a chance with the Event Hub implementation that I know that you want to do the full rewindable, and that's really good, but is there a chance you could sort of release that code in stages so that I could get an early look at the Event Hub?
Absolutely. That's why I also wrote it this way. Like, first try to do something simple, like not the rewindable, a simpler one. Release that, and then later on, like, keep working on the rewindable. Yes, that is our plan. I don't want to like now promise dates.
Yeah, sure.
But we do have that right in our code. It's just kind of tangled with some other code, and well, Sergey has something to say.
Could you at least sort of give me an idea in terms of a quarter? I mean, could I expect it by the end of the year, for instance?
Sorry, I missed the question.
By quarter or by the end of the year?
Yeah, we can promise, I guess. The simple one, yeah, we can promise. It shouldn't take months. No, it should be quicker. But also, someone just in the community like a couple of days ago said, like, "Oh, I'm going to write it." It's actually not too complicated.
Yeah, I think that was.
If you look at the Azure Queue adapter, right?
Yeah.
That's why we came up with this notion of adapters. Like the whole heavy lifting is done in this base class. But the adapter itself, you look at Azure Queue adapter, it's pretty trivial. I mean, it's not. It's easy to write this one. So writing a Event Hub Queue adapter should be very easy. So if maybe someone will write it quickly, if not, we will write one. It shouldn't take months.
Let me take a look at it, and because I'd love to, you've given, I'd like to give something back, but I am very new to the whole Orleans project, so I can't promise that I'll be able to do it to the correct standard, but I'd certainly give it a try.
Absolutely. Sounds great.
Any other questions?
Yeah.
Anybody has other questions?
Yeah. So we encourage you, to start using, as I said, the Azure Q1 and a simple message Q1, simple message stream provider. You can use it around. You can write application. We will publish more samples. Like there's already samples in GitHub.
but there are more interesting samples that we can write, and we will create those. And also documentation. There's much more documentation now, but again, like just ask us like what is not clear, and we'll evolve documentation and add more.
I also wanted to clarify one more thing. So, with releasing this code of the Event Hub adapter, it's not like we have something and just we decide when to share. No, we want to share it as soon as possible, that all of you guys can jump in and improve it and extend it, so can I have the basic implementation that we came up, just like with the Orleans code base. You have very different experiences, very different perspectives. That would help us. So it's not intended to be like one-way road. It's the opposite. That's why we want to solve, we want to remove all these dependencies on services code that kind of crippled in because of rush for Halo 5 beta. We want to remove all these things that can have application dependencies and then release as quickly as possible. It's not like we'll be sitting in it and deciding, oh, we're going to release it by the end of the year. No, the sooner the better for us. Just wanted to make sure that's clear.
Yeah, that's cool.
So, seems like there is another question. Oh, what happened with my camera? Hey, Katie, you have a question?
Yeah, I have a question. I imagine the case when, for example, I have, I don't know, millions of event-sourced actors and each act like the stream. And with virtual streams, I'll probably have the same count of virtual streams, and probably that will be additional overhead. What do you think for that scenario? It makes sense to just build kind of a streaming functionality into the actor itself and not use virtual streams? What will be the benefits, for example, in that scenario for using virtual streams instead of just like trying to build something on top of observers?
So you mean streams
you want streams that basically once like grain activation like died, then you just automatically unsubscribe? That's what you mean by not virtual? Or because this is virtual, like it has multiple options here, the multiple like meanings. Is decoupling on space and time. If you don't need that decoupling, you don't need to decouple producer and consumer, then you don't need the whole pub sub. Like that's one thing. Maybe you want that, but not the eternal subscription model. So what do you mean exactly?
Yeah, I mean we have virtual actors already. Now we have virtual streams, and if my actor acts like a stream already, like producing an event, and maybe it will be just more efficient to build kind of a streaming functionality into the actor itself and not use the virtual streams. Something like, I don't know, using observers, things like that.
So okay. So efficiency. So if I compare, for example, for SMS, right, with direct messaging. So there is the overheads. There's two overheads. One is the whole pub sub, that like trigger, remember who subscribed to what, and then there's the delivery. So the pub sub can be eliminated because if you have this implicit subscription, you don't need to. It's basically like static time kind of defined. Okay, and even if you do use pub sub, there's only one call that you make when you subscribe, when you produce a first event. So the pub sub is kind of like a meta operation that happens only once for every, for every actor. So pretty cheap, and then we can get rid of it completely with implicit. And now you're back to messaging. So if you're just doing like regular actor-to-actor calls in your other implementation, it will be kind of the same. There wouldn't be any extra overhead in the virtual streams. And actually, in the virtual streams, I can have optimized because I have this kind of abstraction and then runtime, I can have much more optimization added in the future. For example, you publish one producer publishes an event to 100 consumers and you're running on 5 silos. We don't need to send 100 messages. We can send 5 messages, right? That's what I call like multicast on the messaging layer. We don't do it now, but we could, and that will be completely transparent, like within the implementation, and anyone will benefit, and you will need to kind of do it yourself. So kind of, so I would say it depends, like what is this other implementation they're coming up with. The other one. In theory, it could be more optimized, and depending on how what you do. Okay.
Okay. Yeah, because there are some interesting cases, like, for example, with rewindable streams. If I have, very long stream, it might be. Let's say another example. I have the actor that is producing events very frequently, and that probably will be, I'd like to shorten the window when I get any events from it. So instead of polling the underlying storage, such as table storage or blob where I store the events, I might just switch to kind of a live streaming from that actor, something like that. And it might be valuable to do some kind of catch up, like if I have a very long stream and I'm subscribing to something with a long history, it might be more efficient to just go to the underlying storage and events in batches, and once I have replayed everything, I might just switch to live notifications coming from the actor.
That's possible. That's possible, but you can also, for example, with the virtual streams, you can have two subscriptions. You have the latest subscription, and then you subscribe another time. That's what I said. You can subscribe multiple times, and then you subscribe another one from the past. So you're receiving kind of two streams in parallel until you catch up, and then you unsubscribe for the first one. And well, yeah. Like from my perspective, I would like, if you have ideas how to optimize certain things, I would like you to suggest them, and we will implement them in the audience virtual streaming runtime, and then if will benefit. If there's something, if there is something that you have idea to implement, and it's not implementable in the runtime, well then yes, it makes sense to implement it yourself. But if it's if I can put this optimization within the runtime, I would prefer.
Okay. Thanks.
So I guess we'll wrap it up. We're already over time, but we started a bit late. Right? So, and I'm not sure what happened with my camera. It shows me upside down. But thank you all for attending. Like I said, there are two goals: to sort of explain this whole confusing thing. Everyone talks about streaming, and then now we're talking about our link streams, to see that it's not just a buzzword compliance. There is some interesting scenarios that we think we can enable with this technology, but also to kind of give you a deeper dive, so that hopefully you will join us and contribute and kind of help shape this effort to a direction that will work for most scenarios and more efficient scenarios. So thank you very much. Hope to see you all on GitHub in future discussions. All right. Stopping now. Thank you.
Thank you, everyone.
Bye-bye.